All right, so the plan for today is just to finish up this last little topic in chapter 2 on log and semi-log plots. To introduce Excel, we're going to go through a very much a crash course. So, you should have gone into Excel already and worked a little bit in it, either through the instructions from the book or through that Coursera course that I had mentioned to you. So Excel should be a little familiar. I'm not going to start with, the complete basics, but just how to do some of the things in chapter 2 that we're looking at, and then start chapter 3. So that is the goal for today. The quote of the day it's a quote that's attributed to Albert Einstein, but, unfortunately, when you're as smart of a guy as Albert Einstein was, a lot of things get attributed to you. So I'm not 100% sure that he actually ever said it or wrote it, but it's attributed to him. So, and the saying is, compound interest is the most powerful force in the universe. And, what's the idea of this? Does this just apply to finance? Well, it applies to finance. I mean, on one hand, you can say, well, invest when you're young and it pays off, greatly when you're ready to retire. But as a general idea, positive feedback in the sense of self-reinforcing phenomena, and we're going to kind of touch on these ideas, exponential growth and so on, in these log and semi-log plots. That's where this kind of correlates to the material for today. Positive feedback or self-reinforcing phenomena or exponential growth or quote compound interest is extremely powerful. So this also ties in with that types of knowledge, the quadrants of knowledge, whether it's static or dynamic and trivial versus foundational, that foundational knowledge can build upon itself in an exponential way. So if I learn one piece of information that helps me learn the next piece, and those two pieces give me a real leg up learning a third or a fourth piece, so I can compound my efficacy of learning that way. So again, small improvements that stack are preferable to larger but disjoint improvements. And note also that powerful things can cut both ways. So this can be beneficial or it can be disastrous. If you lay on the couch for a few days, then what you tend to want to do is lay on the couch more. Or if you eat a bunch of junk food, you tend to want to eat more junk food. And these are things that I don't always make the best choices on. But if you get up and you walk a little bit, it might be tough to walk around the block that first day. You might be a little sore afterwards, and the next day you're a tiny bit more fit, a tiny bit more resilient, and it's a little bit easier to do that same thing the next day, and then a little easier the next day, and so on. So you can that exponential growth can go in both directions. And I would like a little more space here, but I'm worried if I move. I have a whole bunch. These are all different windows, so I'm going to try not to move these windows. So just leave the screen here, and I think we can fit everything on it. Okay, so we talked about scatter plots last time, which was a relationship between two variables plotted on a two-dimensional graph. And interestingly, my wife and I were just talking about flow cytometry this past weekend for some other reason. And so this topic of flow cytometry and the different, how many different CD markers you can look for in one run and so on did actually come up. Okay, so what if we have a plot like this? This is a scatter plot where we have these triangles, these diamonds in blue and the red squares representing some different things. But what's interesting about this plot is if we look at the x-axis, the horizontal axis, we see 25, 30, 35, 40, 45, 50 equally spaced as we would expect. But if I look vertically, I have 2,000 at the bottom, say roughly 4,000 in amount up from that. Then 6,000 isn't, that next 2,000 unit jump, 4,300 to 6,500 is about 2,000. that's not the same distance as 2,000 to 4,000, right? And if you look from 9,000 all the way up to 23,000 up here, that's maybe the same distance as like 2 to 6,000 at the bottom. So on the bottom, we go up 4,000, but near the top, we go up 14,000 or somewhere along those lines. So what's going on here? What's going on here is that we have, in this case, a semi-log plot, or in some other cases, a log-log plot. As I mentioned last time, we're going to take a little bit of a digression into logarithms and exponential functions. If you don't remember this material from Math 108 or equivalent, or maybe you never saw it in Math 108, logarithms are an optional topic in Math 108. Exponential functions are not an optional topic in Math 108, although that is debated amongst our faculty as to exactly what the master syllabus says. The wording is a little bit ambiguous. So something like exponentials and logs can be considered by some faculty to be an optional topic in Math 108. So you might not have seen this before. If you haven't, that's okay. But I'm giving you a little bit of the background just so that you can see a little more, have a little more insight into where these ideas come from. So one thing we had mentioned before is that when I have a scatter plot, it's super nice if I can draw a straight line through that data, that it can act as a model and can do a good job of describing that data. So possibly I have a scatter plot where my data roughly fall along a straight line. And if I call this variable x and this one y, I pick a slope, I pick an intercept, that gives me a line. Y equals mx plus b is my model. That's my relationship between x and y. And let's just suppose the model goes through 0, 0, just to make things easy. That's not all that big of an assumption. We can always just like subtract off. Instead of using x and y, we can do like x minus x bar and y, or haven't quite gotten there yet, but x minus the average of x and y minus the average of y instead. So it's not all that big of a deal to just say, let's just assume if we are modeling with a straight line, that straight line goes through the origin. So this is what we call a linear model. And this is like the simplest model we can write, just a straight line. But then the question is, well, what if my data seem to follow a nonlinear pattern, where, you know, a model like this might be a better model. So what if I had a nonlinear model? What if the natural relation between my two variables was nonlinear in nature? I really don't want to use a linear model to try to capture what's going on here, because that's just not going to do a good job of capturing the important parts of the phenomena. So when I say I have a nonlinear model, that really opens up an entire world of possibilities. But I can get a very good approximation to my data in very, very many cases by using one of two types of models. So the two types of models that are quite often used to try to model nonlinear data are exponential models and either power models, or basically a polynomial with one term, so just a monomial. An exponential model will look like y equals, I'll have some base, say a, to the exponent where the independent variable is in the exponent. So for a linear model, I might have y equals 2x, 2 times x. So whatever my input is, I double it and I get y. For an exponential model, I might have something like y equals 3 to the power x. So whatever my input is for x, I raise 3 to that power, that output is y. Or a power function might look like y equals x to the power of b. So this might be like y equals x to the 1/2 power, or y equals the square root of x, say. Or this could be like y equals x to the 4th power. So whatever value of x, whatever independent variable I plug in, I might square root that, or I might raise the 4th power. I'll raise it to some power to get my output. So these might be two models that are nonlinear models that that I often use to model phenomena that have a more complex relationship that can really be well described with just a line. Now, the unfortunate thing is that how do I figure out what A is? How do I figure out what B is? How do I look at this curvy data and figure out, well, should I use an exponential model? Should I use a power model? Should I use this kind of polynomial model? Which one of these two should I go for? And then maybe how should I figure out what A or B are? Let's assume that, and we don't know this yet, but we will by the end of the course, let's assume that we know how to figure out M in a linear model based on some data. At the end of the course, we'll learn that. But how could I leverage the understanding that I have of a linear model to give me some insight into these nonlinear models? Well, it turns out that logarithms, the natural log, has this really nice property that the natural log of something to a power, the power just comes down in front of the natural log and multiplies it. So if I take the natural log of both sides of this exponential equation, I have natural log of y equals, well, that would be natural log of a to the x power. But this x just comes down in front of the natural log. That's one of its properties. Again, we're not really going into what logarithms are. This isn't, Math 108. And this material on logarithms isn't crucial for understanding scatter plots. But I want to show you where this comes from to give, those of you who are interested some deeper insight. So I have natural log of y equals x times natural log of a, but here a is just a constant. So natural log of a, this is also just a constant. In other words, natural log of y equals constant times x. So if I imagine I have my data, x and y, if I replace the y data, if I keep the x data the same, but I replace the y data with natural log y, I take each data point, I go to my calculator and I do natural log of that data point, that'll give me a different number. That's a transformation. Maybe I'll draw these like as squiggles. If I plot these on a scatter plot, using x as the horizontal axis, and then log y as the vertical axis, if I were to plot x comma log y instead of xy, I would get something that falls roughly along a straight line. So that's really the idea, is if my data are fundamentally exponentially related, if I replace the vertical axis or the y data with its log, then I should recover an approximate linear relationship. If I do the same thing to the power function, or the kind of polynomial function, if I take the natural log of both sides, I get natural log of x to the b comes down in front. And here, well, I guess that's just the end of that. But here I want to replace both X and Y by their logs to recover a linear relationship. So again, I just take each of these data points, both X and Y coordinates, go to my calculator, say, instead of using this number, use natural log of this number. If I plot these, I should get a linear plot. So how do I figure out if I think that my data is nonlinear in nature, if I want a nonlinear model, and if I want to pick between these two models, there may be other things you could pick, like say a sinusoidal function or something more complicated, but these would be good ones to try first. If I want to know which one do I think is best, I would see what happens if I log just the y variable and plot it and see, do I get something that looks like a straight line? Or if I log both variables and plot it, do I get more of a straight line? That's how I pick between the two. Which one gives me data that more conform to a straight line? So these log and semi-log plots, log plot is obviously when both axes are logged, and semi-log is when we have one normal axis and one logarithmic axis. So these log and semi-log plots, you see them come up in finance. We talked before about kind of the issues of inconsistent units and things like, you know, the Great Depression doesn't look all that bad, because if we, you know, just look at the last 100 years of S&P value, it's a tiny little blip, but that's because we're using something like inconsistent units. So in finance, sometimes things are presented on a log scale when they're over a long time period like that. That's one way to try to correct for some of that inflation. In biology, we see semi-log plots. In a situation like this, where we have a gel, we have an agarose gel, we put some DNA into the well in that gel, we apply an electrical current, and what happens is the DNA is, it's not easily able to move through the gel. The gel is a porous medium, so it can make its way through, but it kind of, you know, gets buffeted around, it gets bumped around. The longer the chunk of DNA is, the slower it moves through the gel. So if we run this electrical current through this gel for a specified amount of time, and then we stain the gel, and that shows us where the DNA is, we might get a band like this, and another band like this, and another band like this, and that might tell us that there were 3 lengths of DNA in this well. So we had some DNA that was very large that didn't move very far because it got held up a lot in between those little pores. We had some that was kind of a moderate size and some that was a smaller size. So what this is representing is the distance from the well in centimeters. So it's representing this distance on the x-axis, the distance that a certain chunk of DNA got to, versus how long the DNA is, how many base pairs it is. So it's representing distance from the well in the horizontal axis versus basically the length of the DNA. And this might be important for us to know, you know, what one example of this might be if a person has, say, you know, a normal copy of this gene, it's nice and long. If they have a mutated copy of the gene, maybe we put in an enzyme that for that mutated copy, it sees the mutation and cuts the gene there, cuts the DNA there, and cuts it into 2 smaller pieces. So this might be somebody who has, you know, one bad copy of the gene with the mutation and one good copy of the gene with no mutation. The enzyme, you know, went in and like cut, say, about half of their genetic material with the bad copy and made two shorter pieces that went further down the gel, and then failed to cut the copies that didn't have the mutation, so that one stayed as a bigger chunk and didn't go very far down the gel. So this is what we see over here, is that this process of length of the material related to distance that it travels down the well is fundamentally nonlinear. It's plotted on a semi-log plot. The bottom axis, distance from the well, is a standard scale. The same distance across represents the same increase in distance from the well. So 25 to 30, 35 to 40 are equally spaced distances from the well, each time that increases by 5 centimeters, and they're equally spaced on the graph as well. But going up the y-axis, the number of base pairs, the length of the genetic material, is on a log scale. What's another way to think about a log scale? If we think about what an exponential function does, if I double the input, I square the output. So in other words, going from 2000 to 4000 is a doubling in this vertical distance along the graph. Going from 4000 to 9000 is again roughly a doubling in about the same distance. Going from 9000 to 23,000 is again roughly a doubling in about that same distance. So the 2 to the 4 to the 9 to the 20, that's double, 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 and those are the same distance. So that's how you can tell a log scale. Or it just kind of looks, a little crazy, like it does here. That's what clues us in. And then we look a little more closely and say, okay, yeah, that's on a log scale. So I see I have a semi-log plot because the bottom scale, the horizontal scale, is standard, but the vertical scale is logarithmic. So I'm in a situation like this one here, where my y value is logged, but my x is not. And tracing that back, that suggests that there is an exponential relationship between size of the genetic material and distance it travels from the well. And as an aside, this actually has bigger implications for things like Sanger sequencing and so on. Like once you get out to say 800 or 900 base pairs, it's really, really hard to tell apart those fragments, because the longer the base pair is, the smaller the difference in how long it has traveled over a certain amount of time. So it's really hard to tell, 800 versus 801 base pairs, much easier to tell, say, 50 versus 51, because the distance, the difference in the distance they'll have traveled for the lower numbers is much larger. It's much easier to quote see, or for a sensor to pick up, than for the higher base pairs. So there are a lot of important implications of, understanding that it is a nonlinear relationship, and then all of the fallout from that in both things like finance and in some applications of biology. Okay, so are there any questions on this PowerPoint from chapter 2? Oh, I see there's a question in chat. Can you show me where the Coursera course is? It's on the useful websites tab in Blackboard. Yep, so check that out. Any other questions from chapter 2? Or from the PowerPoint from chapter 2? Okay, let me close that. So I have some Excel spreadsheets that I will post in the chat. These are also, I think, up on Blackboard. I'll double check at the end of class, make sure these are up on Blackboard, but I think these should be. And we'll go through each of these 3 spreadsheets. Oh, here's just some more fun bad graphs. some of these are classic ones, or some of them are ones that I saw on a website and, pull it off or something. But let me shrink this just a little bit so you can get it all. This is, possibly the worst graph of all time. It's even a little hard to see on the screen because it's actually so tall. But this is the age structure of college enrollment on the left here. And then on the left, we see like percent of total enrollment going from like 28 to 34, and then skipping over to 66 to 72. And this is like under 25 on the top and 25 and over on the bottom. I think some college or somebody published this, and it's possibly the most confusing graph of all time, because there's so much going on here and none of it even makes any sense. Like, I mean, we see that like 67 versus 33, 66 versus 33, 70 versus 30. So these are clearly complementary, but they're like, the 70 looks like it's smaller than the 67. This is probably the worst graph of all time. It's one of those ones that like somebody published at some point and somebody screen capped it, and now it just gets passed around as like the worst graphical representation of data, maybe ever to have existed. So if you know the person who made this, they're famous, at least in some nerdy internet circles. But here's another, here are a couple more practical examples. This was from a report on drinking ages across Canada. And for some reason, they decided to make a bar chart of the different drinking ages for all the different provinces. But all of the ages are either 18 or 19. So it's like, what does a bar chart actually do here? Not to mention that the scale is all wonky. Like, at least fix your scale so that you have like just 18 and 19 or something, So it's like, you could have just said, these three provinces have drinking age 18 and the rest have 19. But for some reason, they decided to put it on a bar chart. I don't know why. Here's a good example of the two-dimensional versus one-dimensional scaling problem. If you look at, say, Starbucks over here, poor little Starbucks with only 4 billion in sales, and McDonald's 41 billion in sales. Or if you look at Burger King with 11 billion in sales, you see how these scale, right? Starbucks to Burger King, 4 to 11. Burger King is maybe about 3 times as tall as Starbucks. But because when you scale these and keep them in proportion, keep the aspect ratio the same, when you scale the vertical axis, it also scales the horizontal axis. So if you're showing that Burger King has 3 times the sales roughly of Starbucks, and you choose to make Burger King 3 times as tall as Starbucks, then it's also 3 times as wide, and it looks like Burger King has absolutely dwarfed Starbucks. It looks like Burger King sales are 10 times Starbucks, when really it's McDonald's that are 10 times Starbucks, and McDonald's looks like it's just absurd. But really, it's only about 4 times as the amount of sales of, say, Burger King or Wendy's, maybe 5 times that of KFC. KFC or Pizza Hut, but it looks like it's, it looks like it's like 15 times as big, something like that. So these are just a couple of other bad graphs that didn't quite make it into the PowerPoint, but I thought were kind of funny and interesting to show you. Okay, so let's work on creating graphs of these data. You can use the data analysis tool over here, and the book walks you through how to do that. We're going to do things a little bit more bare bones. So let's first look at this data for the last digit of people's weights. Here we have 2 rows, columns A through Y, so 25 columns. So we have 50 data points. And we see this is the last digit of weight. So I have 50 people, I have their weights listed, and I just took the last digit of each of them. And these are the numbers that I have. The spacing is a little funky because of the how I respace things down here, but so there's no rhyme or reason to the spacing as far as this data goes. So we have different classes, 0 through 9. It makes sense, even though this is numerical data, not really to group it. I'm looking for a bar chart here. And really, I want to know how many zeros do I have, how many ones, how many twos, etc. And we'll see why that is in a second here. So I'd like to make a frequency distribution. I'm going to make one by hand. And again, you can maybe use the data analysis tool to do this a little more quickly. But we will go through the process of making one by hand. So there's this nice function in Excel, equals count. You know, if I pick these cells, why didn't, let me pick these cells. There we go. I forgot it doesn't like text. You need to use a different one for text. But the function count just counts the number of cells essentially that are non-empty or that have, you know, some numerical value in them. So what I would like, I would like to count all of the cells that have the number 0 in them in this data set. So I think the first thing that I'm going to do is I'm going to select all of my data, which I'll do by clicking one corner, holding shift and clicking the other corner. That's a super nice way, instead of clicking and dragging, and then you drag a little too far, not quite far enough, and have to do it again. Click one extreme, hold shift, and click the other extreme. By the way, that is a general Microsoft shortcut. You can click a file, hold shift, and click another file, and that selects everything in between them. So it selects everything in between based on Microsoft's definition of in between, which sometimes can be a little confusing, but here it's pretty clear. I've selected all my data, clicked one corner, shift, click the other corner. I'm going to rename this. I'm going to come up here where it says like 2 rows by 25 columns. I'm going to click that, and I'm just going to call this something like data. Hit enter. Now I can see in this box it says like H3 or O2. That's the name of the thing that I'm looking at, in this case, the one cell. If I go up here and I type data and hit enter, Excel knows that when I type data, I mean this block here, these 50 cells with these 50 numbers in them. That's going to just make it easier for me to reference later. So that's a super nice little trick. Just call your data set data, select it, and rename it data, or something like that, or maybe something a little more descriptive. And then it makes it super easy to do a lot of computations on it. You don't need to keep clicking and dragging or selecting it or whatever. You can just type data. Nice little short name to give it. Now I want to count, but I only want to count if something is true. So the function is called count if. So I want to count all cells that meet a condition, in particular, the condition that the value is 0. Now with just a super quick recap, if I want Excel to do a computation, if I just type in something like 3 plus 7, Excel just looks at these as characters. Just the character 3, just put these pixels here, a character plus sign, put these pixels in this place, and then a 7, put these pixels in these places. If I wanted to do a computation, if I wanted to think of 3 and 7 as actual numbers and plus as a binary operator that adds things, I have to append an equal sign. So I have to put an equal sign at the front. That tells Excel that I want to calculate something. If I'm using a built-in function like count or count if, I start with an equal sign to tell Excel, I'm not just typing the word count because I want you to put these pixels on the screen. I want you to actually do something. I want you to actually do a computation. So I start with an equal sign, I type count if, and just like a mathematical function where I might have f of x equals x squared, and then like f of 2 equals 2 squared or 4, we use parentheses to define the inputs into a function. So count if of, and I see there are 2 arguments. One is the range, In other words, the list of cells that I'm interested in evaluating this function over. And that's what I just called data. So I'll just type in data. And then the criterion. So I want to count the cell if and only if what is true, if and only if it has a 0 in it. I'll close the parentheses, hit enter, and I see that it counts 26 zeros. And that seems about right. There's a bunch of zeros here. If it came 50 or 0, I'd be a little suspicious that maybe I typed something in wrong, but this seems pretty reasonable. Notice that I also have a total down here using the equal sum built-in function. So if I want to count the number of ones, I could go through and type in the same thing with 1 instead of a 0, or 2 or 3 or 4. That's a little tedious. If I am okay with using a little bit of syntax, I want to use that same range, those same cells, the ones that I called data. My criteria can be to say, okay, I want to reference another cell. This is one of the really powerful things in Excel, is that I can use values in other cells as inputs into functions and formulas for different cells. The ampersand character, I know there's a lot of syntax, but the ampersand character just says, I want to reference another cell. I don't want you to like use what I'm going to type in next as actual inputs. I want you to go to this cell and find this data in that cell and use that as an input. So I think you need to have these two quotations, and then ampersand AB4 says refer to cell in column AB and row 4. You might be able to get away without the quotations. I'm not 100% sure. Let's try it. No, it doesn't like that. So we do need the quotations there. So I want to count the number of cells from this range of cells where the pattern matches that pattern that's in cell AB4, which I just got by clicking on it. Now, the really nice thing about Excel is that I don't have to type in another one for AB5 and another one for AB6. I can select my cell, go to my bottom right-hand corner, see where that white big plus sign turns into the small black plus sign. I can click and drag, and I see that Excel has kept that data. It's kept that reference of what cells I want to refer to for my data, but it has adjusted the pattern one. It has adjusted AB4 to, in this case, AB6, referring to the 3 for the class. So again, I mean, if you haven't looked at any of that Excel stuff that I've been saying for the last couple of weeks to look at, this is going to be super confusing. So if you haven't done that, I strongly recommend, again, getting up to speed on that in the next day or so. Use the Coursera course, use the material from the book, use an online tutorial, anything, whatever works for you. And then come back and re-watch this part after you understand it. Because if you don't understand any of that material, you're going to be thinking, what the heck is he doing? This isn't meant to be a bare bones introduction. That's what those other resources are for. But what we have now is
recorded, right?
Is there a question?
No, I'm sorry for disturbing. Like, this is being recorded, right? Plus previous classes?
Yeah, exactly. Yeah, definitely. This is being recorded, so you can go back, and just the same as all the other classes, you can go back either to the YouTube channel or to the Zoom link and rewatch it. So if you need to see this a little more slowly, or if you want to go and kind of fill in those knowledge gaps about Excel and then come back, you can definitely do that. Yep. So now we have our frequency distribution. We have our set of classes 0 through 9. Note that because these are numerical, there's kind of a natural ordering and ranking here. We might debate that, but it's kind of a natural order and ranking. If it's just the last digit of somebody's weight, Is a 9 really bigger than a 0? Not really sure, right? Somebody could weigh 139 pounds and somebody could weigh 170 pounds. And so it's a little less clear, but let's just suppose that it is. So I kept them in that kind of numerical order. We have our list of frequencies. So 0 occurs 26 times, 3 occurs 2 times, 5 occurs 12 times, and so on. And we've checked that the total frequency is the number of data points that we have over here. It is 50. So that's a good check just to make sure that we didn't miss anything, count anything twice, right? It's not a guarantee. I could have missed one and counted and double counted another, but it's pretty good evidence. Now I would like to make a bar chart for these last digits of weights. Now I could do this by hand. Come on, well, no, let me scroll over. There we go. I could do this by hand if I wanted to. I have my frequency distribution, and I'll write a couple of bars. I'm not going to write them all. But if I was going to do a bar chart, I would want to say, okay, well, first, let me look at my frequency axis. The highest frequency that I see is 26. So if I go, I always start at 0. Again, frequencies are definitely ratio data. It's the number of data points that fall in this class. So that's definitely ratio. I want to start at 0. And then maybe I'll go in units of 5. We'll go up to 25. I mean, one of these is 26, but it'll just be a touch above 25 for the height. So 0, that bar is going to have height 26. 1, that bar is going to have height 1. I want to make these about the same width. I'm not an artist. They're not going to be perfect, but I want them more or less the same width. Data value of 2 also has 1 occurrence. Value of 3 has 2 occurrences. 4, also 2 occurrences. 5 has 12 occurrences, so I want a horizontal line about at height 12. Make my box. Your boxes might touch or might not touch. You might fill in your boxes or might not. All of those are just side details. And then of course we keep going 6, 7, 8, 9, 10, or 6, 7, 8, 9. So this is what the frequency distribution would look like graphed as a bar chart, as a histogram, as a column chart, doing it by hand, right? Not too bad to just make one by hand. But we could use Excel to make one for us. I can select my classes and frequencies, and I'll go up here to insert. See, like File, Home, Insert. I'll go to Insert. I would like to insert a chart. You see the little subheader charts down here where all of these are. And unfortunately anymore, they started not writing words on a whole bunch of stuff. I'm not exactly sure why, but we can kind of see, okay, this is our column chart, our column or bar chart or histogram, lots of different names for it. This is our drop-down menu for column charts. We can have like 3D ones or, more complicated ones. But again, I just like the simple ones. And let me actually come over here and just select this data. All the different versions of Excel are slightly different in how they, by default, grab the data for making charts. So if you go and you hover over a chart and you say, so if you did this, and you hover over your chart, you say, oh, that doesn't look right at all. Just go back and kind of adjust and say, okay, yeah, that looks more or less like what I want. So if I click this, it gives me a chart that looks fairly similar to my one I drew by hand, right? It's going to obviously be more accurate, more precise, but it looks right. I can give my chart title. Say last digits of weights. I do notice one thing though, that the y-axis looks good, the vertical axis looks good. You know, I see my height of 26, I see my height of 12. I see a problem though. I should have 26 zeros, but this just says 1. I should have, for instance, a frequency of 0 associated with a class of 7, but it looks like that 0 is associated with something called 8. Well, Excel is just saying this bar represents the first in the list. So the first number observed is a 26, the second number observed is a 1, but really I want to use these as my horizontal axis values, not just the default 1, 2, 3, and so on. So how do I change that? Well, if I right click kind of somewhere, if I right click like on a bar or something, it gives me a different menu. But if I right click kind of somewhere where there's not really anything going on, so just in some white space here, I see it gives me this kind of more full menu. And I want to select data. Now, a lot of the other special menus also have select data. So if you clicked on a bar or something, you'll probably still see select data. But definitely if I click somewhere kind of in the white space where there's not a lot going on, I find select data and I click that. And in particular, I'm interested in this right-hand side here where it says horizontal or category axis labels. These are the labels for the classes. And by default, it just uses numbers starting with 1 and incrementing by 1. I would like to edit this. And I would like to use the axis label range. I'll just click and drag and select these classes 0 through 9. And I see now, right, if I look at my graph, it's already shown me kind of a heads up display. If you click OK, this is what you're going to get, 0 through 9. So if I click cancel, you see it switches back to 1 to 10. When I do this edit and select these, it updates to 0 through 9. That's what I want, so I click OK. OK again. And there's my chart. So again, you can go in here to data analysis, and use histogram. You can go that route too. Now, side note, we did talk about this with a couple of folks very briefly at the end of last class, but I want to go through this in more detail today. Some of you might not have this data analysis tab up here. So let me show you what that might look like. I'll do this really quick just to get rid of that data analysis tab, and then I'll show you how to add it back in. So don't try to follow along with this. So you might go to, here's File, Home, Insert. You might go over to the Data tab, and you might see nothing over here to the right. You might not see that data analysis section with the data analysis tool pack. How do you add that in? Well, and I don't know why Excel does this. These days in the information age, I mean, all of this stuff is already downloaded to your computer. I don't know why they don't just have this added in, but you have to go through these little hoops to add this in. So if you follow along, go to File. If you don't have that, go to File. That'll bring up this menu. Go down to Options, Account Feedback Options all the way at the bottom. On Options, we see like General Formulas, Data, go nearly all the way to the bottom to Add-ins, and click that. And then you see we have some inactive add-ins. Again, I don't know why they're inactive. I don't know why they just don't make these active. They're already downloaded. We want to manage Excel add-ins at the bottom. So that bottom line where it says Manage Excel add-ins, we'll just click Go. And we see there are some add-ins available, and you should have the analysis tool pack available. Just check that box. I also like to check the box for solver. Sometimes that can be a useful tool in other circumstances, or maybe even later on in the course if we wanted to do something a little bit more interesting. Having the solver added in might be helpful. And then just click OK. Give it a couple seconds. And now you should have your data analysis, again, under like home, insert, data up here. You should have your data analysis tool pack added in. So I can click this, and it's going to take it a while to start up because I just added it back in, and you can go through histogram. You can create a histogram maybe a little bit more easily that way. But I wanted to do one of these kind of by hand, just to, number one, demo some of these ideas in Excel for you. And number two, I think it's good to do one kind of by hand a little bit, at least once or twice. Okay, so let's look at another data set. Here we have some data that we want to create a relative frequency chart and a pie graph for. And these are train crash causes. These are labeled as track, equipment, human error, or other, TEH or O. So these are categorical data. These are qualitative data. So I have my four classes, T, E, H, and O. My frequencies, which I'll compute, along with the total, just to make sure, again, I have columns A through Y, so 25 columns, 2 rows. I still have 50 data points for this data set as well. And I could go through and tediously, jot down like, okay, 1T, put a tally next to T, and then cross this one out. And I could do that for all 50, but let's use a count if statement again, equals count if. And I think I'd really like to name this data set, but what if I didn't? What if I didn't call this data or something, or data 2 like I called the last one? I could select my data by clicking, one corner, holding shift and clicking the other corner. That will select all my data for me. I could do it that way. Nothing wrong with that. What's my criterion? I could just type in T. Now, if I do that and I try to drag down, if I can, there we go. If I try to drag down, I see a couple of problems, right? One of the really nice things about Excel was that I could type in this formula, drag down, and I didn't have to type it in a whole bunch of times. It was able to copy things down. It was able to copy cells by reference and so on. I see two problems. When I double click on this one that I dragged down, the one next to E now, number one, my highlighted cells for my data, they're no longer actually, those cells are no longer actually corresponding to my actual data. They're corresponding to something else. Those cells have all shifted down by one because I dragged the cell with the formula down one. By default, Excel always refers to cells by reference. So in this T cell here, it says, okay, go up 1, 2, 3 cells and look at that data. For the E, it's saying go up 1, 2, 3 cells and try to find your data here. But that's not what we want. The other thing is that I want this to be an E instead of a T. There's a couple of things I can do to help out here. One thing I can do is, instead of having my cells put in like this for my data, I can lock my cells. So if you're on a Windows machine, you can hit F4. Don't hit Alt F4, that closes things down. But if you just hit the button F4, that will lock your cells. If you're on a Mac, I'm pretty sure it's Command T that will lock cells. But when you do that, Excel should put a $ in front of each of the column names and each of the row names. Now, there are other fancier ways you can lock cells. You can like lock column and not row, or vice versa. We just want to lock everything. So again, if I go into my track causes, my class T, if I select my cells, and if I hit F4 on Windows or Command T on Mac. Puts all these dollar signs in. Now let me try to copy this down one. Well, now I made some progress. Now, even though I dragged that formula cell down one to copy it, my cells referring to the data stayed the same. Those were locked. Those were passed into the function directly by their value. They're locked in place. They're not relative to the cell that has the formula in it. Now, I do have another problem, though. I want this T to be an E. I could just copy this down and then change the T to an E and then do an H and then do an O. That wouldn't be so bad. But again, if I wanted to be a little more slick about things, or definitely if I had, 20 different train track causes, again, I can refer to the cell immediately to the left. I do not lock that cell because when I drag down, I want my frequency to correspond to the cell directly to its left. So I want that cell that I'm referring to drag down with the frequency calculation. So now I have COUNTIF, I have my data cells locked. I could have also selected my data and given it a name. That would have also been an easy way to kind of lock those cells. But I chose to do it a different way here, just so you can see different ways of doing the same thing. I locked my data, and I'm passing my criterion for counting in as a reference. So now when I drag down, I see that I have the same data set that I was initially using, the data set that I want. And my criterion is now I'm counting whether the data point has a value E. Now I'm counting the H's for the same data and the O's. And I see that my total is 50, so that checks out. Now, what about a relative frequency? So these are the frequencies. These are the number of occurrences in my data set of each of these classes. But what about a relative frequency? What about a percent? What percentage of my data were crashes attributed to track problems? Well, for this, I want to take my frequency divided by my total. And if yours comes up as 0.46, you can come up here to home and then just click the percent option up here, and that'll turn it into a percent. So if you got, say, a 0.46 or something like that instead of 46%, just under home, above number here, you just click percent, and that changes that 0.46 into 46%. Now I might be tempted again to just click and drag, but I actually get something that didn't work so great here. My error message, if I click on, or if I hover over this little caution sign here, I'm trying to divide by 0. What happened here? Oh, okay, so what happened was when I drug down, I did want to refer to the new frequency, but I want to keep the total the same. The denominator that refers to the total should stay 50 the whole time. So really in this first box, when I drag down, so planning ahead a little bit, when I drag this cell down, I do want my frequency, the numerator, to change 23 to 9 to 12 to 6, but my denominator, I want to stay as that 50. I don't want that to change. So I lock that again with either F4 on Windows or with Command T on Mac. Now when I drag down, now it looks better. I know that my frequency should just be like double, or my relative frequency should be double the frequency, but as a percent, right? Because 50 times 2 is 100. And I do see that that seems to work out. I've created my relative frequency chart now. That's a step in the right direction. I need to also create a pie graph. Two ways I can create a pie graph. I can select my frequencies. I can do insert, over here on my charts, I could pick a column chart or a line chart, or I could pick a pie chart. Again, I could pick some kind of crazy 3D pie chart, but with pie charts, we even have a perspective issue that these slices in the back look smaller than they should, and the slices in the front look bigger than they should because of the perspective. So what's the purpose of making a pie chart that's supposed to represent these proportions accurately and then giving you a perspective shift that misrepresents the proportions, right? I mean, it looks a little fancier, but it doesn't make a whole lot of sense to do. Again, I just like this top left one, the bare bones one. It doesn't look super fancy, but it accurately represents the data. I could rename the title. Maybe something like train crash causes. And then I just see like 1, 2, 3, 4 here. I want these to actually be related to the names of the classes. So again, I'll right click somewhere in the white space. I'll find my select data option. My horizontal, or in this case, my category axis labels. My category is my names for the slices. I want to edit that, and I want to use these instead. And I see now it's shown me this is what you're going to get if you click OK. That is what I want. And I can see at a glance that track issues cause about half of the crashes, and maybe, you know, roughly evenly distributed among the other 3 are equipment errors, human error, and other. Maybe with human error being a little bigger than the other 2. But I can see it's something like roughly 50%, and then, you know, 1/3 of the remaining 50% attributed to each of these. You might say that it's like 50%, a quarter, 25% for human error, and then evenly split between the other 2. I mean, you could split hairs as much as you want here, but we can see the relative proportions for the causes pretty quickly here. What if I wanted to create a pie chart by hand? Well, here, the first thing that I would want to do is I would want to figure out what angle should be attributed to, what angle for each slice should be attributed to each class. So here I'll take 360 for 360 degrees in a circle times the relative frequency. So I want 46% of the degrees around the circle to be associated with the pie slice for track causes. I see that's 165. I can click and drag, get 65 degrees for human error, or sorry, for equipment, 86 degrees for human error, 43 degrees for other. One of the kind of crazy things about a pie chart is it's probably one of the earliest charts or graphs that you see, and that, you know, that you become used to interpreting, but actually creating one is not easy. So first we need to draw a circle, which in and of itself is not easy. But if I have track, okay, I need 165 degrees. So 180 degrees would be, if I'm going to say start up here, 180 degrees would be straight down. I need to go 15 degrees less than that. So maybe something like this. So what would I do next? Well, next I would probably say, I'd probably look at my remaining percents and say, which one of these is easy to draw? Well, 25% or 86 degrees, that's pretty close to 90 degrees. I can draw a 90-degree angle pretty easily. So that is what? Human error. And then I look at my others and it's like 12 to 18. I mean, that's pretty close to the same, with the 12 being a little less, or 43 degrees versus 64 degrees. So that is my slightly less one. So that would be other, and then I guess I'd have equipment problems. So it's actually, a bit of a pain to make a pie chart by hand because of all the angles. And, you don't want to have to like go find a protractor or something, get it out and start measuring all these angles. So it's a little bit of a putting together a puzzle, trying to figure out which angles will be easy for me to kind of start with. And then, maybe I see the two angles add up to about 90 degrees. So then maybe I can kind of draw that 90 degrees and then split, down the middle more or less where that split happens. But not super easy to draw a pie chart by hand. And this was only, 4 classes. You can imagine if we had 8 or 9, it would be even more complex. So sometimes Excel is super nice, like drawing our pie charts. Sometimes, if we had this frequency distribution already, it's probably about a toss-up between how hard it is to do in Excel versus how hard it is to make a histogram by hand. So depending on the chart type, it can be easier or more difficult. Any questions on these? Okay, I think that's about what I want to talk about in chapter 2. We didn't really use those other two, the other 2 Excel spreadsheets that I posted. If we have a little time, say at the end of chapter 3, we might come back to those, but those were a little more tangential, more talking about kind of the finance side of things and how to correct for inflation and some of those things that we had talked a little bit about at the end of chapter 1. Are there any questions on chapter 2? The PowerPoint, the stuff we just did, the homework, anything? All right, then in the last 20 minutes or so of class, I would like to start chapter 3, which I've made a little bit of a mess of with my semi-log and log stuff up there, but sometimes if you select a bunch of stuff in OneNote and move it, it like works perfectly, and sometimes it like just completely blows up. So I'm like always afraid to move stuff once I get it the way that I want it to look. Okay, so moving on to chapter 3. Chapter 2 was really all about graphical representations of data, descriptive statistics that are graphical in nature, that are pictorial in nature. And of course, that the prerequisite to that was making frequency distributions to get the data organized so we can easily graph it. Chapter 3 is all about numerical descriptive techniques. So I have a data set and I want to present to you, instead of just one picture representing the data set, I want to present to you one number that's representative of some aspect of the data set. The first section in chapter 3 is measures of center. And this tries to kind of roughly answer the question, something along the lines of, what does the typical data point look like? Like, what is a typical data value in this data set? Now, this doesn't sound very much like a mathematical type of question, right? It's an ill-posed question. There's not going to be only one way to answer this. And that's kind of on purpose, because this question has a lot of nuance to it. And you'll see that there are lots of measures of center, lots of different ways of getting at the answer to this question. Maybe in some contexts, one will be a better option. In other contexts, a different one will be a better option. The kind of 3 main ones that do a lot of the heavy lifting are the mean, the median, and the mid-range. But we also have the mode, the weighted mean and the geometric mean, the harmonic mean, and then there are a bunch of others that have kind of special use cases. One, for example, would be something like, say, the root mean squared. if you've ever done anything with electronics and used, you know, a voltmeter, if you, and don't do this unless you know what you're doing, but if you plug a voltmeter into your electrical outlets in your home, you'll see that the voltage that it gives you, well, that's alternating current. So the voltage is going up and down 60 times a second, but it's just going to tell you a number like 110 or 115 or 120 or something. Well, that voltage is calculated according to a root mean square calculation. And there's a good reason for using this mean, this measure of center, this average for that application, rather than something like, you know, one of these averages. So sometimes there is a good reason to use, say, a particular measure of center, maybe even an offbeat one. In this case, what the RMS is telling you is, if instead of alternating current, if you had direct current, if you hooked this light bulb up to a battery instead of plugging it into this outlet, what would the voltage of the battery need to be to make the light bulb shine equally bright? So it's saying, okay, if this was direct current instead of alternating current, if it was a constant voltage, what voltage would you need to have the same power output as you get from this varying voltage? So sometimes there's a good reason to use one measure of center over another, and sometimes maybe it's not very clear which one is the best, and you have to make a decision. Okay. All right, so and also throughout chapter 3, we're going to be using these 3 data sets. We have some salary data here. We have some tax returns completed per day here for 2 different people. And we have some shirt color observations, just listed as a frequency distribution here. Also raw data listed here, but color of the shirt, red, green, yellow, or blue against the frequency. And note that this will become important in the next section, but salaries we're thinking of as a sample, and tax returns we're considering as a population. There will be no way to know just by looking at a list of numbers whether it represented a sample or a population. So this is something that I'm telling you, and that's the only reason that you know it's one or the other, is because I've just told you here. Okay, so let's start looking at these 3. We'll probably get through these today, maybe not completely, but at least through most of them today, and then we'll pick up with the rest next time. So the most important, the mean, aka the average, or if we want to be more explicit, the arithmetic mean. So how we have things like the geometric mean or the harmonic mean. If we wanted to be very clear which one we're talking about, we would say the arithmetic mean. Stats textbook writers make a big deal about not calling the mean an average, not just referring to it as the average. And their argument is, well, there's lots of types of averages, but there's also lots of types of means. So I don't know. I'll probably call it the average half the time and the mean half the time, especially because Excel, the formula is equals average. So like, I'm not nearly as picky about that, but you know, just know that somebody somewhere has decided that the grammatically correct term is mean instead of average. But we might call it the mean, the average, the arithmetic mean. Yeah, so I think Jesse said something in chat that gets at an important point here. So Jesse said salaries median, tax returns per day mean, shirt color mode. So yeah, that touches on an important point as to why we might choose one measure of center over another in different contexts. And we'll definitely get to that, but that's a good point though. So the mean, how do we compute the mean? Well, let's suppose from this point forward that we have a data set that it consists of n data points. And a data point will have kind of a label saying if it's the first data point or the second or the third data point, and it'll also have a value. So a data point has kind of the number of data point that it is in the data set, as well as the value. So the first data point might have a value 10, the second point might have a value 6, the third data point might have a value 10 again. Different data points can have the same value. So we have n data points, and we'll label them x sub 1, x subscript 1, x sub 1, x sub 2, x sub 3, all the way out through x sub n. So if we had 10 data points, this would be x1, x2, out through x10. And we compute the mean by adding up the values of all of our data points. If we have multiple data points with the same value, we add that value in multiple times. If I have 3 data points that have the value 10, then I have 3 lots of 10 being added up. And I divide by the number of data points added together. If I have a class of 20 students, if I have 20 grades from the midterm exam, I add up those 20 grades, I divide by 20, that gives me the average grade, that gives me the mean grade on that exam. So this is the calculation. I add up all my data points values, and I divide by the number of data points that I have, by the number of values that I added up. Now there's a little detail here about notation. Some of our measures have kind of a certain, like almost a trademarked notation. If you see this notation, it means this thing. So that I don't have to write out mean or something every time I want to discuss this measure. Now recall that sometimes we're dealing with the population and sometimes with a sample. So I could be talking about a sample mean, I could be talking about a population mean. These two have different notations. The sample mean has a different notation than the population mean, even though their calculation is the same. If you gave me a sample of, so many data points with certain values, I would compute the sample mean like above, like I listed above. Same thing if you gave me a list of data points and you said this represents a population, I compute the population mean with the same formula, add them all up, divide by the number I added up. Same formula for both, but they have different notations. And really the reason for this, it might seem like a silly thing now, but when we get to chapter 7 and 8, even chapter 6, we're going to be really interested in saying something about how good of an estimate the sample mean is for the population mean. And we're going to have sample mean notation and population mean notation in kind of the same formulas. So we really need to use different notation for these so we know exactly which one we're talking about in which context. The sample mean, my data points are kind of given the name X, so X1, X2, X3. The sample mean for this data is an X with a line over it. So capital X with a line over it, or we'd say X bar. That's our sample mean. If we say that this data came from a sample, or this data represents a sample, when I calculate its mean, I would compute X bar. So in other words, X bar equals this, where these are a sample. My population mean, now my sample statistics tend to use American letters or Roman letters. My population parameters, they tend to use Greek letters. So my population mean is this symbol. Let me redraw that. That's a little messy. So this symbol is mu, the Greek letter M. Probably more accurately pronounced moo, but if you say moo all the time, then people laugh because it sounds like a cow. So we'll call it mu. So this thing, it looks a little bit like a U. with kind of a tail on the left. And the bottom of the line would be like here. So the kind of tail goes below the bottom of the line, but we usually just kind of write it wherever. So this Greek letter mu, again, same calculation, but in the context where our data represent a population. So mu is the population mean, X bar is the sample mean. The calculation for both of them is the same. So let's calculate some means. So here we have, let's say, two folks working for an accounting firm, Ashley and Brandon. And Ashley completes for a given week this many returns each of the days, Monday through Friday. Monday, she completed 5 returns. Thursday, she completed 11 returns, and so on. And similarly for Brandon. Now these are, let me copy this down too. This is important. These represent a population. Again, no way to know that just looking at the data, but we're told that here. So let's compute Ashley and Brandon's mean number of returns per day. I have 2 different data sets here. So I'm going to say for Ashley, I'm going to use a mu with a little subscript a, just to kind of denote that this is the mean, the population mean for the Ashley data. And I see this is going to be 5 plus 8 plus 9 plus 11 plus 7 divided by 5. I see that 9 and 11 is 20, 8 and 5 is 15, or sorry, 8 and 5 is 13, plus 7 is 20. So this is 40 over 5, or this is 8. Now, something that I should note is that my data points, often the values come along with a unit. So we might think of this unit as something like returns per day. So this might be like 5 returns per day, 8 returns per day, and so on. When I add up the same unit, I get 40 returns per day. Note that the 5 is just a counting number. It doesn't have any units associated with it. It's just the number of data points that I have. So this is just a counting number, no units there. 40 returns per day divided by 5 is 8 returns per day. My mean has the same unit as the original data. This will become a very important detail in section 2. Brandon's mean if we do the calculation, turns out to be the same. Again, with that unit of returns per day. Something very important about the mean is that it can happen that the mean or the average or this answer to what does the typical data point look like, it can be actually a member of the data set. It's possible. But usually it's not, right? Usually the mean, when or the whether it's the sample mean or population mean, usually is not actually a member of the data set. It's possible that it can happen by chance, but usually it's not. So when I say what does the typical data point look like, and I try to answer that with the mean, I don't want to take that question too literally, right? Quite often the mean is not the typical data, the typical data point. That mean is not actually a member of the data. What is the mean? Well, what the mean is basically if I imagine a rod that's weightless, where I have kind of an axis. If I, let's say, take Ashley's data, if I put, say, a 1 kilogram mass at location 5, a 1 kilogram mass at 7, at 8, so I'm putting a 1 kilogram mass or 1 pound or whatever you want at each of these locations represented by her data values. There's a 9 and an 11. The rod is weightless. I have these 5 1 kilogram masses at different locations. Where would I put a balance point to make this balance? In this case, I would put that balance point right under 8. That's the center of mass. So the mean is literally the center of mass when we think in this context, where each data point gets ascribed a certain mass or a weight value, and the data value is the location of that. The mean is the center of mass of those masses or those weights. So Brandon would be the same, except his would be a little more spread out, right? He would have a mass down here at 3, but also one up here at like 14. So kind of on average, they both perform the same. In other words, across this entire week, Ashley and Brandon both got 40 total returns done. Or if across this week, if instead of getting the variable number of returns, sometimes some good days, some bad days, if they had gotten exactly the same number every day and completed the same amount of work across that whole week, they would have completed 8 returns per day. So if we kind of cut off the mountains and use those to fill in the valleys, things average out to 8. So that's the mean. That's the most important measure of center. It'll come up over and over and over again throughout the course. And it's probably also kind of, in a sense, the most basic one. You've probably computed an average a ton of times in your life, and you probably understand intuitively what this calculation looks like. But maybe there were a couple of details here that you didn't really think about. Whether the mean necessarily has to be a member of the data set, the connection to the center of mass in the physics sense. So when we come back, we will compute the mean for the salary data, and then we'll move on to talk about some of these other measures of center. So I'll end the recording.